Dear students, a hearty welcome to massive open online courses in chemistry on SWAYAM. In the previous module, you have learnt about the nature of colloidal state, classification, preparation and properties of colloids, mechanism of micelle formation and cleaning action of soaps. After going through this module, you will be able to describe the colligative, optical, physical, mechanical and electrical properties of colloids, to understand the important processes such as Tyndall effect, Brownian movement and electrophoresis, to know about the protection of colloids, to classify emulsions and describe their preparation and properties, to list the uses of colloids. Let me briefly introduce this module. Apart from discussing the properties and protection of colloids, important processes such as electrophoresis, coagulation and protection of colloids will also be discussed. We shall also learn about emulsions, a class of colloids. These find extensive applications in food processing, detergent, pharmaceuticals and plastics. Some examples and applications of colloids are also mentioned. Now, we shall discuss various properties exhibited by colloids. Number 1. Physical property. Although heterogeneous, the particles of colloids cannot be separated by filtration. Colloids are generally stable. Number 2. Colligative property. Colloidal particles being bigger aggregates, the number of particles in a colloid is comparatively small as compared to a true solution. So, the values of colligative properties such as osmotic pressure, lowering of vapor pressure, depression in freezing point and elevation in boiling point are of small order as compared to values shown by true solutions at the same concentrations. Number 3. Optical properties. Tyndall effect and color are the important optical properties. Now, let us start with the Tyndall effect. If a homogeneous solution placed in dark is observed in the direction of light, it appears clear, and if it is observed from a direction at right angles to the direction of light beam, it appears perfectly dark. Colloids viewed in the same way may also appear reasonably clear or translucent by the transmitted light, but they show a mild to strong opalescence when viewed at right angles to the passage of light. That is, the path of the beam is illuminated. This effect was first observed by Faraday and later studied in detail by Tyndall and is termed as Tyndall effect. As you see in the figure, when a colloidal solution is subjected to a beam of light from a source and then viewed through a microscope, we can see the bright cone of the light and is called Tyndall cone. The Tyndall effect is due to the fact that colloidal particles scatter light in all directions in space. How the scattering of light illuminates the path of the beam in the colloidal dispersion is shown in the figure. Tyndall effect can be observed during the projection of picture in the cinema hall due to scattering of light by dust and smoke particles present there. Tyndall effect is observed only when the following two conditions are satisfied. Number 1, the diameter of the dispersed particles is not much smaller than the wavelength of the light used, and number 2, the refractive indices of the dispersed phase and the dispersion medium differ greatly in magnitude. Tyndall effect is used to distinguish between a colloidal and true solution. Zygmundi in the year 1903 used Tyndall effect to set up an apparatus known as ultra microscope. An intense beam of light is focused on the colloidal solution contained in a glass vessel. The focus of the light is then observed with a microscope at right angles to the beam. Individual colloidal particles appear as bright stars against a dark background. Ultra microscope does not render the actual colloidal particles visible, but only observe the light scattered by them. Thus, ultra microscope does not provide any information about the size and shape of colloidal particles. B. Color. The color of colloidal solution depends upon the wavelength of the light scattered by the dispersed particles. The wavelength of the light further depends upon the size and nature of the particles. The color of colloidal solution also changes with the manner in which the observer receives the light. For example, a mixture of milk and water appears blue when viewed by the reflected light and red when viewed through the transmitted light. Finest gold salt is red in color. As the size of the particle increases, it appears purple, then blue and finally golden. Number 4. Mechanical property, Brownian movement. When colloids are viewed under a powerful ultramicroscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view, as shown in the figure. This motion was first observed by the British botanist Robert Brown and is known as Brownian movement. This motion is independent of the nature of the colloid, but depends upon the size of the particles and viscosity of the solution. Smaller the size and lesser the viscosity, faster is the motion. The Brownian movement has been explained to be due to the unbalanced bombardment of the particles by the molecules of the dispersion medium. The Brownian movement has a stirring effect which does not permit the particles to settle and thus is responsible for the stability of salts. Number 5. Electrical property, charge on colloidal particles. Colloidal particles always carry an electric charge. The nature of this charge is the same on all the colloidal particles in a given colloid and may be either positive or negative. The molecules of the dispersion medium have equal but opposite charge so that the system as a whole remains neutral. The colloidal particles repel each other as they carry same charge and do not aggregate together. Hence, the sol as a whole remains stable and the colloidal particles never settle down. A list of some common sols with the nature of the charge on that particle is given in the table. As is clear from the table, hydrated metallic oxides, basic diesters, hemoglobin and oxides of metals carry positive charge. Metals, metallic sulfides, acid diesters and salts of starch, gelatin, etc. carry negative charge. The charge on the salt particles is due to one or more reasons. Number 1 being electron capture by salt particles during electrodispersion of metals. Number 2, preferential adsorption of ions from solution. Number 3, formulation of electrical double layer. Amongst these three, preferential adsorption of ions is the most accepted reason. The salt particles acquire positive or negative charge by preferential adsorption of positive or negative ions. When two or more ions are present in the dispersion medium, usually preferential adsorption of the ion common to the colloidal particle takes place. This can be explained by taking the following examples. A. When silver nitrate solution is added to potassium iodide solution, the precipitated silver iodide adsorbs iodide ions from the dispersion medium and negatively charged colloid results. Instead, when potassium iodide solution is added to silver nitrate solution, positively charged salt results due to the adsorption of Ag plus ions from dispersion medium. It is expressed as Agi/I minus, which is negatively charged, and Agi/Ag plus, which is positively charged. B. If ferric chloride is added to excess of hot water, a positively charged salt of hydrated ferric oxide is formed due to adsorption of Fe3 plus ions. However, when ferric chloride is added to sodium hydroxide, a negatively charged salt is obtained with the adsorption of OH minus ions, that is Fe2O3, Fe3 plus, which is positively charged, and Fe2O3H2O/OH minus, which is negatively charged. Having acquired a positive or negative charge by selective adsorption on the surface of the colloidal particle as stated above, this layer attracts counter ions from the medium, thus forming a second layer as shown below, that is AgI/I minus K plus and AgI/Ag plus I minus. The combination of the two layers of opposite charges around the colloidal particle is called Helmholtz electric double layer. According to modern views, the first layer of ions is firmly held and is termed fixed layer, while the second layer is mobile, which is termed diffused layer. Since separation of charges is a seat of potential, a difference in potential occurs between these layers. This potential difference between the fixed layer and the diffused layer of opposite charges is called the electrokinetic potential or zeta potential. The presence of equal and similar charges on colloidal particles is largely responsible in providing stability to the colloidal solution. This is because the repulsive forces between charged particles having same charge prevent them from coalescing or aggregating when they come closer to one another. Number 3, electrophoresis. The existence of charge on colloidal particles is confirmed by electrophoresis experiment using the apparatus as shown in the figure. You can see from the figure, when electric potential is applied across two platinum electrodes dipping in a colloidal solution, the colloidal particles move towards one or the other electrode. The movement of colloidal particles under an applied electric potential is called electrophoresis. Positively charged particles move towards the cathode, while negatively charged particles move towards the anode. When electrophoresis, that is, the movement of particles, is prevented by some suitable means, it is observed that the dispersion medium begins to move in the opposite direction. This phenomenon is termed electroosmosis. Number 4, coagulation or precipitation or flocculation. The stability of the leophobic salts is due to the presence of charge on colloidal particles. If somehow the charge is removed, the particles will come nearer to each other to form aggregates, or you can say coagulate, and settle down under the force of gravity. The process of settling of colloidal particles is called coagulation or flocculation of the salt. The coagulation of the leophobic salts can be carried out in the following ways. Number 1, by electrophoresis. The colloidal particles move towards oppositely charged electrodes, get discharged and then coagulated. Number 2, by mixing two oppositely charged salts. Oppositely charged salts, when mixed in almost equal proportions, neutralize the charges and get partially or completely coagulated. Mixing of hydrated ferric oxide, which is a positive salt, and arsenious sulfide, which is a negative salt, bring them in the coagulated forms. This type of coagulation is called mutual coagulation. Number 3, by boiling. When a salt is boiled, the adsorbed layer is disturbed due to the increased collisions with the molecules of dispersion medium. This reduces the charge on the particles and ultimately leads to settling down of coagulated particles. Number 4, by persistent dialysis. On prolonged dialysis, traces of the electrolyte present in the salt are removed almost completely and the colloids become unstable and ultimately coagulate. Number 5, by addition of electrolytes. When excess of an electrolyte is added, the colloidal particles are coagulated. The reason is that colloids interact with ions carrying charge opposite to that present on themselves. This causes neutralization, leading to their coagulation. The ion responsible for neutralization of charge on the particles is called the coagulating ion. A negative ion causes the coagulation of positively charged salt and vice versa. It has been observed that generally the greater the valence of the coagulating ion added, the greater is its power to cause coagulation. This is known as Hardy-Schulze rule. In the coagulation of negative salt, the coagulating power is in the order Al3 plus greater than Ba2 plus greater than H plus. Similarly, in the coagulation of positive salt, the flocculating power is in the order FeCN6 4 minus greater than PO4 3 minus greater than SO4 2 minus greater than Cl minus. The minimum concentration of an electrolyte in millimoles per liter required to cause coagulation of a salt in 2 hours is called coagulating value or precipitation value. The smaller the quantity needed, the higher will be the coagulating power of an ion. Coagulation of lyophilic salts. There are 2 factors which are responsible for the stability of lyophilic salts. These factors are the charge and the solvation of the colloidal particles. When these 2 factors are removed, a lyophilic salt can be coagulated. This is done by adding an electrolyte or by adding a suitable solvent or by adding both. When solvents such as alcohol and acetone are added to hydrophilic salts, the dehydration of dispersed phase occurs. Under this condition, a small quantity of electrolyte can bring about coagulation. Now, let us come to the protection of colloids. Lyophilic salts are more stable than lyophobic salts. This is due to the fact that lyophilic colloids are extensively solvated. That means, colloidal particles are covered by a sheath of the liquid in which they are dispersed. Lyophilic colloids have unique property of protecting lyophobic colloids. When a lyophilic salt is added to the lyophobic salt, the lyophilic particles form a layer around lyophobic particles and thus protect the latter from electrolytes. Lyophilic colloids used for this purpose are called protective colloids. The protective power of lyophilic colloid is expressed in terms of gold number. It is defined as the minimum amount of protective colloid in milligrams which prevent a color change from red to violet of 10 milliliter gold salt by the addition of 1 milliliter of 10% sodium chloride solution. The more the gold number, the lesser will be the protective power of the lyophilic colloid. Now, let us see what do we mean by emulsions. These are liquid-liquid colloidal systems, that is, the dispersion of finely divided droplets in another liquid. If a mixture of 2 immiscible or partially miscible liquids is shaken, a coarse dispersion of one liquid in the other is obtained, which is called emulsion. Generally, one of the 2 liquids is water. There are 2 types of emulsions. Number 1, oil dispersed in water, which is known as O/W type. And number 2, water dispersed in oil, which is called W/O type. These are depicted in the figure. In the first system, water acts as dispersion medium. Examples of this type of emulsion are milk and vanishing cream. In milk, liquid fat is dispersed in water. In the second system, oil acts as a dispersion medium, and common examples of this type are butter and cream. Emulsions of oil in water are unstable and sometimes they separate into 2 layers on standing. For stabilization of an emulsion, a third component called emulsifying agent is usually added. The emulsifying agent forms an interfacial film between suspended particles and the medium. The principal emulsifying agents for O/W emulsions are proteins, gums, natural and synthetic soaps, etc. And for W/O, heavy metal salts of fatty acids, long chain alcohols, etc. Emulsions can be diluted with any amount of the dispersion medium. On the other hand, the dispersed liquid when mixed forms a separate layer. The droplets in emulsions are often negatively charged and can be precipitated by electrolytes. They also show Brownian movement and Tyndall effect. Emulsions can be broken into constituent liquids by heating, freezing, centrifuging, etc. Now, let us see the colloids around us which we see in our day-to-day life. Most of the substances we come across in our daily life are colloids. The meals we eat, the clothes we wear, the wooden furniture we use, the houses we live in, the newspapers we read are all largely composed of colloids. I shall now give the interesting and noteworthy examples of colloids. Number 1, blue color of the sky. Dust particles along with water suspended in air scatter blue light which reaches our eyes and the sky looks blue to us. Number 2, fog, mist and rain. When a large mass of air containing moisture is cooled below its dew point, the moisture condenses on the surface of these particles forming fine droplets. These droplets being colloidal in nature continue to float in air in the form of mist or fog. Clouds are aerosols having small droplets of water suspended in air. On account of condensation in the upper atmosphere, the colloidal droplets of water grow bigger and bigger in size till they come down in the form of rain. Sometimes the rainfall occurs when two oppositely charged clouds meet. It is possible to cause artificial rain by throwing electrified sand or spraying a sol carrying the charge opposite to the one on the clouds from an aeroplane. Number 3, food articles, milk, butter, halwa, ice creams, fruit juices, etc. are all colloids in one form or the other. Number 4, blood. It is a colloidal solution of an albuminoid substance. The styptic action of alum and ferric chloride solution is due to the coagulation of blood forming a clot which stops further bleeding. Number 5, soils. Fertile soils are colloidal in nature, in which humus acts as a protective colloid. On account of colloidal nature, soils absorb moisture and nourishing materials. Number 6, formation of delta. River water is a colloidal solution of clay. Sea water contains a number of electrolytes. When river water meets the sea water, the electrolytes in sea water coagulate the colloidal solution of clay. This results in its deposition, leading to the formation of delta. Let us study the applications of colloids. Colloids are widely used in the industry. Following are some examples. Number 1, electrical precipitation of smoke. This is carried out using a precipitator known as Cottrell precipitator. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, dust, etc. present in air. The smoke, before it comes out from the chimney, is led through a chamber containing plates having a charge opposite to that carried by smoke particles. The particles on coming in contact with these plates lose their charge and get precipitated. The particles thus settle down on floor of the chamber. Number 2, purification of drinking water. The water obtained from natural sources often contains suspended impurities. Alum is added to such water to coagulate the suspended impurities and make water fit for drinking purposes. Number 3, medicines. Many medicines are colloidal in nature. For example, argyrol is a silver sol used as an eye lotion. Colloidal antimony is used in curing the disease called Kala Azar. Colloidal gold is used for intramuscular injection. Milk of magnesia, an emulsion, is used for stomach disorders. Colloidal medicines are more effective because they have large surface area and are therefore easily assimilated. Number 4, Tanning. Animal hides are colloidal in nature. When a hide which has positively charged particles is soaked in tannin, which contains negatively charged colloidal particles, mutual coagulation takes place. This results in the hardening of leather. This process is termed as tanning. Chromium salts are also used in place of tannin. Number 5. Cleansing action of soaps and detergents. This has already been described in module 3. Number 6. Photographic plates and films. Photographic plates or films are prepared by coating an emulsion of the light sensitive silver bromide in gelatin over glass plates or celluloid films. Number 7. Rubber industry. Latex is a colloidal solution of rubber particles which are negatively charged. Rubber is obtained by coagulation of latex. Number 8. Industrial products. Paints, inks, synthetic plastics, rubber, graphite, lubricants, cement, etc. are all colloidal solutions. Now, let me sum up the entire module briefly. Colloids exhibit striking colligative, physical, mechanical, optical and electrical properties. A very important optical property is Tyndall effect, and it is due to the fact that colloidal particles scatter light in all directions in space. When colloids are viewed under a powerful ultra microscope, the colloidal particles appear to be in a state of continuous zigzag motion all over the field of view. This movement of colloidal particles is known as Brownian movement. The movement of colloidal particles under an applied electric potential is called electrophoresis. When electrophoresis is prevented by some suitable means, it is observed that dispersion medium begins to move in the opposite direction. This phenomenon is termed electroosmosis. The process of changing the colloidal particles in a sol into the insoluble precipitate by the addition of some suitable electrolytes is known as coagulation. Emulsions are colloidal systems in which both dispersed phase and dispersion medium are liquids. These can be of oil in water type and water in oil type. The process of making emulsion is known as emulsification. To stabilize an emulsion, an emulsifying agent or emulsifier is added. Soaps and detergents are most frequently used as emulsifiers. Colloids find several applications in industry as well as in daily life. With this, we have completed the important chapter, Surface Chemistry. Thank you.